Okay, back again. I realized the other day after making the Earth regarding the giant impact hypothesis and the intro with the great X-Men theme song that the computer did not pick up the sound. So unless you had the volume really high, you could probably not hear the theme song to X-Men going on in the background. But you could see me goofily dancing in the side, so I hope you got some enjoyment out of that. All right, let's see. We're switching gears, and rather than this large early catastrophe to early Earth, we're now through the course we're going to focus on these smaller catastrophes that have occurred on Earth. That are really, I guess, more difficult to rank on what has been worse and what has been better overall for Earth. But what I intend to allow to begin to emerge is not really a focus on life, but to have life in the background. So now we're going to be able to start talking about events that have actually impacted life. So during the giant impact hypothesis, there's very likely nothing living on Earth. Life had not gotten its start. Maybe later in the course, we will talk about some of the hypotheses for origins of life on Earth, but there is no evidence from that time, and it would be really hard to preserve any evidence if there was life at that time. So really, we have no evidence of life before that, so it's meaningless to really talk about if the giant impact hypothesis had an effect on life. But today, we're going to be able to focus on a different event. Actually, two events that are related to what we might refer to as ice ages, or I like to call this the deep freeze. So for the introductory picture today, I think this is really great. This is a picture taken from above the Arctic Circle, where you can watch the sun during the summer months skim the horizon. So the sun never sets above the Arctic Circle. As you watch it rise and then set, it never actually sets below the horizon. I can see this doesn't really show up very well in this bleached out screen. So if you're a student that's enrolled in the course, of course you have access to all of these slides on the Canvas website. And for anybody else who's stumbled upon all of this material and you want to keep watching this or this video, you can actually find all of this lecture material, all the PDFs to these presentations on my website. I'll put a link in the bottom of the comments on this video, and probably should have done that to previous videos. But that's thismagicalearth.com, and magical is with a C and a K, so MAGICKAL, This Magical Earth. But today's event, I wanted to show this great picture of above the Arctic Circle of the sun never setting, not specifically for the seasons, though we'll touch on that a little bit today, but the topic of deep freezes, or the topic of ice ages, I think contrary to popular thought, is really tied very closely to solar radiation, and we'll go through that in the next half an hour or so. Another early primer in this video that I should mention is that I've tried to break this into 3 different segments today. So I'll stop the video, that'll be a good stopping point, and then we'll start a separate segment rather than doing this all in one long hour and a half long run, okay? All right, so today, or this week in Violent Earth, we're focused on deep freezes, the global deep freeze. First here, we'll go over the idea of climate, or the concept of climate, and what that means. We hear a lot about climate in our modern media today, and I think that many people have a lot of misconceptions about climate, quite unfortunately, because it is so important. It is so important, particularly because of global climate change and a terminology, or also global warming, as it sort of used to be called, terminology that entered the common vernacular maybe about 2, almost 3 decades ago in the late 90s, early 2000s, and it really became a politically hijacked scientific concept. which has led to these great misconceptions. I mean, they're not great as in great, wonderful. I mean, great as in huge, whoppingly huge misconceptions about climate just in general. So I'm not going to take all of that on, but I'm just going to sort of focus for a few minutes on defining climate. Then we'll then start to focus on what actually is the climate forcing, right? What actually causes these changes that we see in longer term geologic climates that lead to ice ages. And then lastly, I want to go over a few climate regimes, and then we'll pick up there and bite off a little bit heavier topic of the Pleistocene glaciation in the next video. All right, this is kind of a spiral view of where we've been. In one of the first videos, we focused here on the cosmic web and the relationship of beyond our heliosphere, beyond our solar system, and these interesting pattern relationships that show throughout the accretionary disk and the formation of our solar system, during the ignition of the star in the center of our solar system, the sun, we refer to it. And then we did also focus on the concept of the layered Earth. This is an image that was used in that lecture, but that also resurfaced as we were talking about the giant impact hypothesis. So because the iron core that had differentiated or developed during the early Earth, the pre-giant impact Earth, and also the neighboring sister planetesimal Theia, they both had some sort of layering to them, quite likely. And then they exchanged some amounts of those materials during that impact, which has led to, of course, Earth's gigantic core and Moon, or Luna's very small core. So this is actually a really good example of how some of these earlier foundational concepts in Lecture 2, layering, chemistry, basic mineralogy, and rocks, are going to keep resurfacing. So at any point, via the videos or the PDFs that are online, anybody can revisit those earlier lectures to keep brushing up on that as we keep speaking about these. Okay, so this is where we have been. The trajectory of where we're going is yet to be determined. So what is climate in the first place? Climate is defined as, I guess let's first distinguish weather, right? Weather is what is going on in the atmosphere right now. All right, so right now, as I look out the window in the back of the classroom, it's a sunny day. It's probably 42, 45 degrees outside Fahrenheit. It's a nice winter day, though this is January. We had a little bit of precipitation last night, liquid precipitation, and we're sitting at about 45 degrees latitude. So for Northern Hemisphere winter, I thought that was a pretty neat meteorologic phenomena or weather phenomena. So those are examples of weather. It's sunny outside. It's windy right now. It's raining or it's snowing. The current conditions of the atmosphere are what we define as weather. Now, if we're looking at that phenomena through time or any longer time period, we then are talking about climate. So we do have on Earth, because of different factors we'll talk about in a second, we have seasons. So we have seasonal variation or seasonal climates. You expect in the Northern Hemisphere for it to be cold and maybe snow to fall in Northern Hemisphere winter in January, February, March, meteorologic winter. Where in the summer you would expect maybe triple-digit temperatures in the Northern Hemisphere or really high humidity in the southeast United States. So those are examples of weather phenomena that we expect because we know the climatic variation. We know how that that geographic area, behaves through time. Why? Well, maybe you lived last year and you noticed last year that's what happened, and then that's what's happening this year. But same thing, those observations that are extrapolated beyond lifetimes. And beyond lifetimes, I mean that farmers or agriculturalists have been taking these observations for hundreds of years in the very rigorous recording sort of way. And then also for longer than that, for thousands of years, these things, meteorologic phenomena, are written in maybe story form, in journals, personal journals, and things like this. So we actually have a really good understanding of how weather has changed over the last, let's just say 1,000 years, right? Because we have some of these grains that have been written down about variation in weather. And that variation in weather through time is what we refer to as climate. So those are examples of maybe daily climate, right? Where it's cold, it's warm at noon and then it's cold at midnight. Or seasonal climate, which would be it's cold in January, but it's warm in July. Or we can then start talking about more decadal or century-long climates, which are a lot more abstract for our human mind because we tend to think in hours, in days, in weeks, and in years, maybe in longer 5-10 year frames of mind, especially the generations. But what we are referring to more in the scientific perspective of climate, we generally focus on when we're talking about global climate change, you're talking about climate variation on decades and centuries at the very beginning. And what we're going to get to today is talking about climate on the order of thousands and millions of years, right? That's what I'm interested in. And here in Violent Earth and in geology in general, we're interested in the really long changes that have occurred in Earth. So we're going to focus on, or we're going to take a look at some of these long-term climate variations. So this image behind me here is a climatic map, or these bioregional climates, or biomes sometimes they're called, as they exist on Earth today. Now, this is probably average data over, say, a couple of decades, and those couple of decades inherently look a little bit different than the couple of decades before that, as maybe some of these biomes have shifted a little bit, and we expect these to also change in the future. That's just climate change in general, global climate change, and we'll address in a little bit the anthropogenic portion of that. So what is shown in these various colors here, in the green you have tropical climates that you would maybe expect near the equatorial latitudes where you have higher amounts of precipitation, higher or more moderate daily temperatures, and both of those things allow what we refer to as tropical vegetation, right? Just your typical rainforest tropics type of thing. Now on either side of those tropics, we tend to see the world's deserts near the 30-degree latitude north and south of the equator areas. The large deserts of the world, the Atacama Desert, Patagonia Desert, the Sonora Desert here in the desert southwest United States, the Sahara Desert, and the Australian Desert, and so on. Those areas tend to have descending air that is very dry, air that's coming after the tropics have allowed that air to well upward to the top of the troposphere. There's a convergence zone or dropping air that occurs around those 30 latitude, and that air is just really dry. It doesn't have a lot in it. Doesn't necessarily mean hot. A desert isn't necessarily hot. What defines a desert is a very little amount of precipitation. So little amount of water that nothing can grow, or very little can grow. So water is life, and you need to have access to water to have voluminous life. So these are these patterns, right? In the tropics, you expect tropical trees, right? Tropical environments, tropical animals, tropical plants and biomes. And in the 30-degree latitude area, you expect more desert ecologies, right? That's what we're talking about with climate. This is repeated year after year, that area has the same daily and seasonal or yearly variations of the same weather phenomena. So all together, we refer to that as climate. So a long-term average of the regional weather that is due to a few different factors, right? Could be geographical factors like proximity to bodies of water, could be topographic factors, and so on. All right, so when we're talking about climate, we're really talking about a region's average weather conditions. Okay, so these are a few of those the factors that may impact those repeated regional type of phenomena. On the top up here, these are a few images that are from the local General Science 109 meteorology class that's taught here. And this is a textbook by Aaron's Essentials of Meteorology by Cengage Learning. And what is shown in these two top diagrams here is the difference between two cities that are located either slightly inland or on the coast. So here, I believe this must be San Francisco. What's shown here is this variation in annual variation in temperature that's a lot less extreme in the red line up here, a lot less extreme than in the red line a little bit further inboard in Sacramento, where it's a little bit further away from the Pacific Ocean. So the implications that you can draw from this is the oceans act as sort of a thermal buffer, right? Because they are really good at absorbing and then slowly releasing that solar radiation from the sun. That when the sun goes down at night, the ocean still has a lot of that solar radiation to release. So in coastal areas, or really in areas where you have, or where there's a close proximity to large bodies of water, they can be thermally regulated by those larger bodies of water because they release the solar radiation more slowly. And that's good evidence by these two locations. Then if we go down to the middle image that's here, this is a topographic variation. So here's some coast mountains. Here's sort of another range of coastal range mountains in California. Then you have the much larger Great Valley before you rise up even higher topographically to the Sierra Nevada. And then on the east side of the Sierra Nevada is, of course, the Nevada desert, a very good classical desert here in North America. Now, I think it's very familiar to people that we have the rain shadow effect. And the reason the rain shadow effect occurs is this air that's being pushed upwards topographically over this orogenic rise. As that air is being pushed into higher and higher elevations, it's colder the higher you go. And that temperature drop forces the water that's there in the air to condense and to form cloud droplets, which then can eventually coalesce and form rain droplets or precipitation. So it is the elevation change of this water that's beginning here, the atmospheric water that's beginning from the ocean, across up the elevation. The drop in temperature causes that precipitation, so some of the moisture comes out of the atmosphere. Now, as that air then descends down the other side, the descending air is warming as it is going through a higher pressure regime. It is allowed to expand, and that expansion is warming. So you end up with warmer and inherently drier air because it is drier. It dropped its precipitation on the leeward side. So descending drier and warmer air, and then that also in this case hits another mountain range. So we have another rain shadow effect, squeezes just a little bit more moisture out, and then all the way over here to the Sierra Nevada, we have another great last squeeze of all the moisture, most of the moisture that exists in this material. And then that descending air, again, that warm, descending, dry air is what moves across the Nevada desert, or the Great Basin area that has very little precipitation within it. First of all, proximity to bodies of water may affect a region's climate, or again, its daily weather, averaged through time, its climate. Then orogenic or topographic rises would affect an area's climate. So if we look at some areas specifically, San Jose has a specific difference in its regional climate than, say, Bishop, California, right? They have, you would expect two different temperatures in the middle of the summer. You would expect two different likelihoods for your chances of rain in the fall season. So those climactic differences once again. Then in a slightly larger, more global perspective, this image is starting at the equator here in the center and then going towards the polar latitudes on either side here. And this is what I was referring to as the convergence zone. Here, the warm air near the tropics is rising with that precipitation, and then at that boundary where you have masses of air that are rising, undergoing condensation again and precipitation, a lot of those tropical storms. But then that air, as it circulates and moves to more northern latitudes, it is allowed to then descend, and it's that descending drier air that causes the global deserts. There's a similar cell, so this is one of these or sorry, I should go the other direction, one of these climactic cells. But then there's also similar cells at mid-latitudes and polar latitudes where we see very similar climactic or very specific climactic conditions. Okay, so hopefully this gives a good idea of climate in general, rather than thinking about the much grander scale climate changes that we are now becoming interested in, either as a human society because of our anthropogenic effects of climate on climate, but also in this class, is that when we're talking about climate, that is what determines what makes Boise, Idaho different from Los Angeles, California, right? Is they have two fundamentally different climates. And it's these type of factors, these geographic factors, that often lead to those differences in climates. Well, what about the larger, the longer term perspective? And besides these simple geographies, what makes climate different and vary over the much longer time frame? Okay, and one of those factors is, of course, solar radiation. And those are the underlying factors that are involved in even these global factors mentioned before, is solar radiation, the amount of particles or photons from the solar wind, as we talked about in the last video during the formation of the solar system, all of that solar energy that is created by hydrogen fusing in the core of the sun. It's the amount of that stuff that actually bombards the Earth. That's really what is driving the Earth being hotter or less hot, cold in some of these areas. And then it's also the cycling of those differences. So anywhere where you have one area that's warming up more and another area that's maybe not receiving quite as much radiation, there's a gradient between those, hot to cold, and that gradient has to balance out, right? That's just like any pot of water. If you're warming up water near the bottom of the pot, that warm, buoyant water will rise to the surface and then replace the cold water that'll sink down. And this sets up what we call convection cells, just like is happening in the mantle of the Earth, because the core is more higher in temperature than the outer portions of the crust. So we have these convection cells that are allowing heat to be transferred from the interior to the exterior. Well, similarly, convection cells drive global weather, or drive global meteorologic changes. And that can be shown here in sort of the first order on the last slide. We're looking at these changes from the equator to polar latitudes. But then if you also involve the rotation of the Earth and what's called the Coriolis effect, then we don't have just these nice little simple cells as was shown in the two-dimensional direction, but instead we have these what are referred to as Hadley cell and the Ferrel cell and the polar cell to also equally distribute those temperatures. So you have the cells that are going from north to south as the solar radiation is changing in those locations, but you also have the rotation of the Earth underneath of that atmosphere. Okay, so it really comes down to variations in solar radiation. All right, this is what's happening right now. Okay, and so in some ways you could almost think of this last decade or this last century on the geologic scale as just as weather. I mean, it's not, it's still climactic variations, but this is just one small little slice of time in the much larger perspective of the Earth and its climactic variations. So it's all about solar radiation and that influence from the center, the heliosphere. Now, there's one thing that I have not mentioned here that is on everybody's mind, which is carbon dioxide or CO2. So when I say climate today, many people jump directly to the influence of anthropogenic emissions or anthropogenic carbon dioxide emissions. which I think is probably an okay thing for awareness in general. But if you don't balance that awareness with all of the rest of knowledge about climate, then sometimes that leads to these great misconceptions that I think today maybe what I've found in teaching over the last decade is folks do associate carbon dioxide with the main driver in the changes of climate, because today anthropogenically we're releasing so much more carbon dioxide than the natural emissions of volcanism. Last numbers that I remember reviewing is we release about 34 gigatons or billion tons of carbon dioxide annually by our types of emissions, where volcanic emissions still remain at about 0.5 billion tons per year. So really we're about 70 times more release of carbon dioxide. Now, my point there on that little tangent is just to say that carbon dioxide is really, really, really important on the much shorter time frames of climatic variation. But it is not the sole factor in overall climate changes. That's solar radiation. And we actually see that in our seasonal variations or even our daily variations in climate, the difference between noon and midnight. Okay, now, but I do want to address carbon dioxide, and we'll address this much further in the course as well in Violent Earth. But carbon dioxide, what is its role here? And of course, most people can immediately think of that role as a greenhouse gas. I can see that I got some kind of little cowlick or thing sticking up here. It's kind of bothering me. Here, I'll make it worse. Carbon dioxide is a greenhouse gas. What that means is it's a selective absorber of different types of solar radiation. So that solar radiation isn't just one thing. It's not just one spectrum of light, the electromagnetic radiation, or the electromagnetic spectrum. Different types of light can carry more energy on that wave. So you have much longer wavelengths and much shorter, higher frequency wavelengths. And the amount of energy associates with each of those. Carbon dioxide is a selective absorber of different types of those frequencies. And carbon dioxide is really good at absorbing the infrared spectrum, or the spectrum that is slightly shorter than 400 nanometers wavelength. So it's carrying a little bit more energy than what we refer to as the visible spectrum of light. And so infrared is, if you've ever seen movies like, say, I immediately go to Predator. I don't know why. I think I saw it on the shelf the other day. Predator can see infrared, right? Or when you see images of what a dog might see, that's infrared light, or the ability, or like say a pit viper, the ability to see the heat that's rising from something. Heat is a signature, or the release of heat is infrared radiation. So you and I, people, we cannot see infrared, but if we could detect infrared right now in this image, my arm would be emitting more visible infrared light than say my torso, because my torso is insulated. So even in touching my skin here compared to here, you can feel the difference in temperature. So there's more infrared radiation being released to the surrounding atmosphere from my arm as opposed to my torso. So going back to carbon dioxide, it's a selective absorber of infrared radiation. Now, it's a selective absorber of other portions of the electromagnetic spectrum as well, but we'll focus on infrared. And that particle, carbon dioxide, just like referring back to water being able to absorb solar radiation, then slowly release it like a battery, carbon dioxide does the same thing or a similar thing with infrared radiation. So if it's out here in the atmosphere, which it is, naturally, totally naturally, carbon dioxide actually in Earth's past was most of the atmosphere. In Earth's, I call it the second atmosphere of Earth, was mostly carbon dioxide, kind of like Mars's atmosphere today, or even Venus's atmosphere today. It's mostly carbon dioxide, which is, of course, not today. That natural carbon dioxide in the atmosphere, the solar radiation that comes in bombards that particle of carbon dioxide, and that carbon dioxide instead of solely reflecting that off and bouncing that material off, it can absorb that energy, which gives the particle more energy. So maybe it starts out with low sluggish energy and then it gets bombarded with some of this infrared light and it gathers more energy. Now, if you have all of the particles in the atmosphere that have a lot more energy, that's higher temperature. Okay? Temperature is actually a measure of the kinetic energy of the particles. So cold water, the particles of water have lower amounts of energy, so they're not moving as rapidly, where warm water or hot water is vigorously moving atoms and particles around. So where that fits into so that's the greenhouse perspective, actually, is that these selective absorbers, not only when the infrared light comes in are they selectively absorbing that, but also as the Earth is naturally re-emitting that radiation back out to the atmosphere after it's absorbed some, there's a secondary effect of carbon dioxide where it absorbs some of that infrared radiation that was re-emitted from the Earth. So this is kind of, I make the analogy to a blanket, right? If you're in your house and you have the thermostat set to 68, 72, I don't know what you set your thermostat at, there's a couple of things that are happening there that are kind of regulating the climate inside your house, right? You have walls, for one. The walls are preventing the inside from being evacuated of its energy, or all of the warmer, more vigorous air from bouncing outside of your house and becoming the same temperature on the inside as it is on the outside. So that, in the case of winter anyway, I'm just thinking it's cold outside right now, so winter. So you have walls, those are kind of the first order insulator, but then you also typically have a heater, right? Maybe you have an electric heater or radiators or forced air, something like this. There's some method of warming the air that's within that capsulated space. And if you have a thermostat that tries to regulate that temperature, the temperature gets down to a certain amount and the thermostat kicks on, pushes out more of that warmer air, it warms the air more, and then it turns off. And you sort of have a natural variation in those two. Now, there's one way to change your overall climate in your house, and that's to change the climate of your body, your physical warmth, and that's to change the thermostat level, right? But you can also just simply put on layers, right? You can put on a sweatshirt, you can put on a blanket, and that's going to work more immediately to help your needs. The thermostat and the heater, that might take, there's a lag time, maybe 5-10 minutes for the area to warm up, but that blanket is going to work immediately to help you as an individual preserve your heat. So carbon dioxide is much more like a blanket that helps sort of the Earth regulate that temperature variation. Now, the analogy isn't perfect, right? The carbon dioxide is also a little bit more like a thermostat thermal regulator. So again, the analogy isn't perfect, but I hope that sort of works, is that solar radiation is the main driver of climate, or is the main driver of how warm or how cold the Earth is, right? How high or how low your thermostat is. But carbon dioxide serves as a buffer. Carbon dioxide serves as kind of a blanket to the Earth to allow it to regulate that temperature from going to two extremes. So, well, let's leave it at that right now as carbon dioxide being a greenhouse gas, and it works sort of like a blanket to the Earth, as the whole atmosphere does, to keep all of this stuff habitable down here. Or the effect is that the surface of the Earth is habitable because of these atmospheric compositions. Okay, carbon dioxide does not drive the overall climatic differences that we looked at in that very first image of the world. It doesn't drive where the deserts are at. It doesn't drive where the tropics are located. Okay, that's totally solar radiation. But carbon dioxide does help buffer those differences as solar radiation is going through dramatic changes. Okay, so imagine that we had no carbon dioxide or no atmosphere. When the sun goes down, it would get down to negative 400 degrees at night if we had no atmosphere or no selective absorbers like carbon dioxide. And then when the sun comes out, it would swing back in the other direction. There would be major temperature swings because of the lack of these particles in the atmosphere. And we don't have that type of system. Instead, we have a regulated system with atmospheric particles, one of those being carbon dioxide. But the factor that does drive climate is solar radiation. So it really all boils down to the fact that we have different variations in solar radiation. And that's actually the reason for the seasons. Here we just went through the Christmas season. We just went through the winter solstice, right? The time of the year where the sun is lowest in the sky. The days are the shortest then. And now after the winter solstice, we start to see the sun or the solar radiation is returning. Slightly longer days doesn't really mean it's warmer necessarily yet. But inevitably it will become warmer as the sun spends more time in the sky. And the reason for the variation in seasons is solar radiation. Now, hopefully you remember back to the reason that we have northern and southern hemisphere differences in seasons is the tilt of the Earth on its axis. And that's going to be one of the factors of the change in large geologic solar radiation is the change of this axis. So right now, today, the Earth is tilted about 23.5 degrees on its axis. And during Northern Hemisphere winter, the Northern Hemisphere is tilted away from the sun. But as we swing around or we revolve around the sun, in July, Northern Hemisphere is going to be tilted towards the sun. So there is more solar radiation bombarding the Northern Hemisphere in the summer than in the winter. There's very little solar radiation bombarding the Northern Hemisphere. And that's the main reason for why we have the winter and the summer seasons here on Earth. Okay, now the solar system is not perfect. Okay, there's nothing that's perfect, right? And I don't really know what perfect means. There's probably nothing that is the definition of some sort of perfect. I think perfect is probably more of a perception than anything. But really, the solar system is not perfect in any way that you can maybe make a solar system diorama or anything like that with these nice perfect circles and all the planets are spaced out perfectly or some measured perfect amount. That's just not how it is. The solar system, there are all these really major effects that are happening between the gravitational orbit of each of these planets. So they each affect one another in these relatively small ways. And then each of them have these inherent, I don't want to call them flaws, but these inherent, during the formation of the solar system, they still have some of those weird asymmetries in their orbit from the very beginning, from the birth of all of these planets. And I really like this view. This kind of shows kind of how maybe our perception of the solar system is a little bit skewed. This is Pluto, the dwarf planet, or now today called the dwarf planet, that exists way out on the edge of the solar system. And it has a wacky orbit. Look at this thing. It is inclined, 25 or more degrees from the rest of the planets, from the ecliptic of the rest of the planets. So that's kind of odd, but if you just even take out Pluto and you look a little bit more closely at the others, they are all actually, their ecliptic is a little bit off. So if you take the equator of the sun and you draw a line outward from that, the planets aren't all within that plane. They're all sort of skewed off a little bit. This reminds me, I brought a hula hoop today, right? Once teaching this class, I kept saying during this lecture, I should have a hula hoop to show this. And sure enough, one of my students, Gabby, brought me a hula hoop one day. So this hula hoop right now seems to be pretty level, at least in the video, from what I can see. And that would be maybe this perfect system where everything is level with the equator of the sun. But instead, we have these skewed planetary orbits around the sun. Okay? So the solar system is not perfect. Here's a couple of ways in how these individual planets have variations. The orbits are not actually circular, right? My hula hoop here is relatively circular, and they're not circles. I mean, you know, on a grand scale, they're pretty darn close, but they're actually ellipsoids, which means kind of a squished circle, or more of what we might think of as an oval. Looks like there's a bend in this. They're more of a squished circle, where instead of having one center to this circle, an ellipse actually has two foci, right? And the further that you squish this thing, the further those two foci move away from each other. Now, it turns out the sun is pretty close to being, on these ellipsoids, it's pretty close, at least for the rocky planets, of being, of splitting the difference between both of those foci. It's pretty close. But the point still stands that the orbits around the sun are not circular. They're ellipses. Okay, so that's sort of thing number one to keep in the back of your mind. Then all of those orbits, they're not in one plane, as we've already discussed. Not only are they inclined individually, but they're all inclined to one another as well. And then those planets, as we mentioned with the Earth, almost none of the planets are vertical. They're not upright, right? Some of them are actually tilted like almost 90 degrees, like Uranus. Uranus is, I think it's over tilted. It's like 97 degrees. 90 degrees would be straight on its side, but it's even a little bit more tilted than that. And its orbit, rather than being you know, straight up or slightly tilted and rotating this way, it's on its side and it rotates in this direction. Really, really cool planet. Now, Earth, however, is also not upright, 23.5 degrees, and that's what gives rise to the seasons. Okay, so let's start looking at then just specifically Earth and some of these variations in the orbit that affects the amount of solar radiation that reaches the Earth. Okay, after all, that's what we're talking about here, trying to get to, is the amounts of solar radiation. First of all, the orbital eccentricity. As I suggested, the orbits are ellipsoid in shape, but also that ellipsoid kind of shifts around a little bit, where the foci of the sun kind of goes back and forth, or the ellipsoid goes back and forth as the foci being, or sorry, as the sun being on one foci and then on the other. Okay, and then there's a slight change in the eccentricity of each of those orbits through time. So here's a good example of that, if my hula hoop example didn't work for that perfectly. In one of these examples, you can see that the difference between those two, right? There's a shift in each of these orbits, but that's not the same distance as the shift on this side. So first of all, one of these orbits is a little bit more elliptical than the other. And then also there's a shift in their relative position where the sun is not at the center. Now this is exaggerated, right? This is not to scale. This is exaggerated to show the point very specifically. To the eye, this distance is 150 million kilometers. This is not something that an astronaut would notice. Say if you sat on Mars and you observed this throughout a couple years, not going to notice it, right? It is only the detailed observations taken that astronomers have taken with telescopes and detailed logs over hundreds of years that this has even been noticed in the first place. Okay, so this is not, this observation is taken from Earth by plotting the sun and plotting the positions of the other planets in relation to the other stars in the background. Okay, a whole bunch of very detailed, careful observations taken through optical astronomy. Nobody has ever stood back on top of the solar system and watched this grand scheme happen. Instead, this all happens through observation and then mathematics of those observations. So this is number one. The orbital eccentricity changes. How does that affect solar radiation then? Well, first of all, there's the effect of how far the Earth is from the sun in this ellipse, where you have the closer side, that's the anhelion, and then there's the axis that would be the shorter axis, or sorry, the longer axis, the perihelion. I think that I have those correct, and that I think I probably don't say those correctly, right? I usually read these things and then say these things incorrectly. But either way, the anhelion and perihelion, today during winter, oddly enough, the Earth is the closest physically to the sun that it is all year long. Wait, did I just say in the winter the Earth is closest to the sun? Yes, that's correct. But remember, in northern hemisphere winter, we're tilted away from the sun. So we're receiving less solar radiation on the surface of the Earth, even though we are physically closer. So what I'm saying is the seasons or the tilt is outweighing the effect of the distance between the sun and the Earth. Okay? But over these longer geologic timescales, that actually makes a difference, right? After all, we're talking about the effect, the accumulative effect to make an ice age, rather than just a seasonal effect, which makes one day warm or 1 month warm and the other month cold. So you can imagine that when the Earth is in conditions like this, where it's a slightly more squished ellipsoid, and then that ellipsoid is also shifted a little bit, so we have some portion of the year where the sun is where the Earth is way further away from the sun than it is in other portions. Inherently, then, this regime of the Earth would be receiving much less solar radiation than this time. Okay, and that happens in a cycle. This is a cycle of about 100,000 years. So every 100,000 years, or well, half of that, every 50,000 years, we see extremes of each of these. So the cycle of 100,000 years, the orbital eccentricity, we see changes of solar radiation because of this effect at a peak or at a minimum, right? Or at a top, a peak and then a trough in solar radiation by just this effect. Now, there's another effect. There's actually going to be 3 of these in total. Another effect called the precession. And this was first named as because of precession of the equinoxes, or the equinoxes moving during the year. Okay, kind of weird, but let me explain that before I explain the phenomenon here. So once upon a time, we had a calendar called the Julian calendar. And that Julian calendar, this was when the solar year was derived, and the year had 12 months, and they're all separated into 30 or 31 days. And just to make it just perfect, to be all split up to measure time, essentially. And the equinox, or the spring equinox that happens in March, or around March 20th, that was, of course, a very important time for agrarian societies. And this is, 1,000 years ago. And that time, planting crops was really important. So noticing the day of equal balance between dark and light, which is what the equinox is, was extremely important for knowledge of planting crops, right? And then if you put that on top of a calendar, rather than just observing this or waiting for when the day is, once you pass the equinox, you have much fewer chances of frost after that. Now, it depends on latitude, of course, but if you could, instead of take that on, say, somebody who's observing these processes and knowing when that's happening, but if you could plan on it, if you could plan work on it, like how many people you needed to help you plant, and put it on a calendar, that was a much easier way to organize people's time if we knew a calendar date. So that's all great to have a calendar, right? A solar-based calendar. But because the solar system is not perfect, there are these weird asymmetries that happen that affected that calendar. So what was noticed in the Julian calendar was that the equinox began to drift. It began to be a precession of the equinoxes. The equinox started to come earlier and earlier every year on the calendar. So that means the actual day of darkness and light being equal, the equal amount of light, was happening earlier and earlier on the calendar. Now, it wasn't, over like 1 year and then another year. This is over a couple of decades and 100 years, but that really began then to affect the agrarian society's ability to count on after March being able to plant crops, right? If it's happening earlier and you're still waiting until March to plant your crops, then that's way too late, right? And then that also pushes you against the first frost on the other side. So you can imagine that this really impacted people's daily lives. So we had the invention of the Gregorian calendar. It wasn't just an invention out of a hat, but by careful observations of the planets, it was then, or of the sun and solar luminosity, it was then noticed that to counteract this precession, if there was a system of adding days into the calendar to offset this, so it would drift, and then let's offset it to put it back. And then if it drifts, let's offset it and put it back. And that's what we know today as leap year, right? Every 4th year, we add 1 day into the calendar. So February was cut down to 28 days, and then every 4th year, we add in a 29th day so we can counteract that drift. Okay, but it doesn't stop there, right? If it would be great if just 1 day solved it all. Furthermore, every 100 years, this was derived back in back in the year 1600. I think might have been the very first of these. It was to counteract drifting too far. Every 100 years, we are to skip the leap day. Skip the leap year. So that means that every 100 years, 1600, 1700, 1800, 2000, we would be skipping, adding the 29th day of February. Aha, but it doesn't stop there even, because that, as this drift comes back and we get a little bit shorter every single time, right, is that's also causing some sort of drift. So every 400 years, you skip the skip of the leap day. So 1600, 1700, 1800 all had a skip of the leap day. But in the year 2000, that was supposed to be on the 100-year mark. We were supposed to not have the 29th day of February. But because of this system, we skipped the skip of the leap day. And in the year 2000, we celebrated February 29th. And everything is now correct on the calendar. Oh my gosh, that was just like a long, interesting explanation. Hopefully it's interesting. There's a little bit of human history in there and how observing the heavens actually makes a difference in our daily lives. It's what affects our calendar. Okay, so that's the history behind the precession. But what is the actual phenomenon? What actually causes this thing? There's kind of 2 parts to this precession of the equinoxes, and the first one is really well shown here in this image. Here's the sun, and this is again greatly exaggerated here, but here's the sun at one of the foci, and as you can see, here's the original ellipse, but over time, that ellipse is actually drifting, right, through time to counteract. So that means that the anhelion and the perihelion are relatively staying the same, where in the previous one they were not staying the same. So if we hold the eccentricity still, and instead look at this instead changes the position around the orbit where the equinox and the solstice occur, right? Instead of the equinox and the solstice occurring in this portion of the calendar, if this twists over here, then you would have summer solstice happening on the calendar winter solstice, right? So that's why the calendar had to be shifted. And for these days, because we don't take the calendar, you can't just mark off where January and February, all these things are on here. Instead, we have the perspective that the calendar is based on the tilt of the axis. The calendar is based on when the peak in solar luminosity happens in the summer, or the sort of lowest amount of sunlight in the winter, northern hemisphere winter. So that's the first factor, is that the ellipse actually rotates around one of its foci. Really cool. That's apsidal precession. And then there's also the axial precession. Both of them have essentially the same effect. Because if here we're worried about the tilt of the axis being in different locations over this long 26,000 year cycle, that's also then impacted by, or impacts the actual position of the Earth, making sort of a circle as it wobbles on its axis in this image. If instead of looking at the whole thing, if you were to look at just the Earth, right, what essentially happens is, just as I was saying, here are the conditions, or the conditions today. Right now, where here's January, Northern Hemisphere tilted away, July tilted towards, but in 11,000 years, half of this cycle, July would be on the other side of the sun, okay? So what we have here is this long 26,000 year cycle that has been counteracted by our method of calendar dates, which I think is pretty cool. But nonetheless, this does have an effect on solar luminosity then, right? So if you have portions of the year that are receiving more or less solar radiation, then you have a greater chance for colder summers. If you have colder summers, then that means less of the glacial ice is melting from the year before. Less of it's melting. If less of it is melting, and then more falls next winter, and then the next summer you have less melting, that leads to an overall growth in glacial ice. Okay, so that's how this would overall affect solar luminosity. Now, lastly, planetary obliquity. Okay, again, we're tilted on our axis at 23.5 degrees, but it's not that way all the time. Okay, which I think is really cool. This planetary obliquity has actually been noticed and is monitored. It doesn't change all that fast. This is also about a 41,000 year cycle that occurs, but the angle, the tilt, changes between about 22 degrees and 24.5 degrees. This should say 22, it's 22.1 degrees and 24.5 degrees. So there is a change in that tilt. So again, if it's 23.5 today, but if we were 24.5 tomorrow, that would mean that this winter would be more extreme because we would be more tilted away from the sun, receiving even less solar radiation than we are already at 23.5 degrees. So again, this leads to colder summers and potentially warmer winters then on the other side of that, right? On the 22 degree side, if it's more upright, then you have more of a constant temperature throughout the year. Okay, so it is these three major cycles that I focused on today. These are what are called the Milankovitch cycles. Milankovitch, named after a Serbian mathematician that really figured all this stuff out, right? And again, it's close astronomical observations that really helped to lay all the foundations to have all these observations. And then Milankovitch was able to go through a lot of this data and to pull out these signals, right? These are essentially sinusoidal wave signals of when we have peaks in solar luminosity and minimums in solar luminosity. So the analogy here is made to a top spinning and wobbling before it falls over. And the Earth has sort of this, these several factors that it is wobbling, which ultimately have an effect on the amount of solar radiation that the Earth receives over not just decades and centuries, but over thousands of years, right? 100,000 year cycle in the eccentricity, a 26,000 year cycle in the precession, and a 41,000 year cycle in the change of the obliquity, or the change in the axis. So these Milankovitch cycles are fairly well known now today, and then it is where those cycles overlap, right? Where the trough in solar luminosity between each one of these things, right? One of them, a 100,000 year cycle, one of them, a 41,000 year cycle, and one of them, a 26,000 year cycle. But each of those things having troughs, right? And where each of those troughs line up, to make the lowest amount of solar luminosity possible, we notice in the geologic record times of ice ages. We notice in the geologic record that alpine and continental glaciation has occurred, and glaciers have scoured areas and dumped piles of rocks called moraines, leaving evidence of these glaciations. And this has happened throughout Earth history. So what's shown here are the climate regimes of Earth. We refer to the ice house as these times of where we have polar ice caps and large polar ice caps that may extend all the way down, in the case of the last glaciation, all the way down to latitudes like to southern Wisconsin or even into Iowa, like the Des Moines Lobe. There's also the cool greenhouse and warm greenhouse conditions, which refer to conditions where we have much less Arctic ice, but there is Arctic caps and Arctic ice that go through seasonal variations. They just don't propagate very far, and they mostly are limited to sea ice unless there happen to be a continent sitting over the poles, like Antarctica. And then there's also the hothouse regime, where there is either no ice cap, right, or there is only a sea ice cap. So hothouse conditions being extremely high temperatures and being very little ice caps or very little ice. And what's shown here is the geologic time scale going from today all the way to about 850 million years ago. And into these blue bars, you can see is referring to an ice house. And the in-between portions are referring to these hothouse-like conditions. And then the white bars referring to these greenhouse-like conditions. So through geology and astronomical mathematics, combining those two, we now have really good evidence that ice ages occur repeatedly throughout time on these much larger grand cycles. So the recent ice age, that we are arguably still in this ice age, the glaciers have receded back for now. But because this is a cycle, the tilt of the axis is we should inevitably head back to that extreme tilt of the axis, and the glaciers should advance back forward, just as they did during the Pleistocene glaciation. They pulsed forward down to latitudes of like Nebraska, and then came back down to latitudes of Illinois, and came back down to latitudes of Wisconsin, and came back. We should see another advance, another great ice advance, if the natural systems and these Milankovitch cycles were to remain true. However, what we are unsure about is anthropogenic effects. How does the major change in carbon dioxide affect all of this? And remember, these carbon dioxide is like a blanket, right? So we've done the analogy of throwing on about 6 or 8 blankets onto ourselves, and we have yet to see how that is going to affect the advance of ice in the next 11,000 years. Okay? Models can only suggest that. I like this image. This was created for Earth Labs project by Lenny Armstrong. But this is the ice house-like conditions and hothouse-like conditions in the form of a yin and a yang. That this really is a yin and a yang. These are both normal, right? This is what Earth has gone through throughout Earth history, is we have advances and retreats of ice ages. Climate change or global climatic change is nothing out of the ordinary. This is what Earth does on its normal behavior. But human conditions, the conditions that humans have grown up in, have been in one short, small band where the ice has mostly been in farther northern latitudes. And we've never seen anything else. Right? Our predecessors, Homo erectus, or even as far back as Australopithecine, have been in much different conditions. But since we've been growing crops and doing agriculture for the last 10,000 years, we have lived in a very narrow band of these conditions. And what we are unsure of, and the reason why global climate change is very important to us, is we don't know how we can respond and our crops will respond to these major changes, okay? And that's really the pinnacle here. We're not ruining the Earth. The Earth does this, right? We're really just ruining ourselves, right? Or our own ability to do business as usual, what we've been doing in the past. We are changing the ability to do the same things that we've done for the last 10,000 years. So it's not that Earth is going off into some territory that it's never seen before. It is the pace at which that is happening is leading to biodiversity loss, as well as the impact on our agrarian society. Okay, so today's dose of violence, as regular, I should introduce here Milan Milankovic. He's the Serbian mathematician and astronomer that really is the foundation of the Milankovitch cycles. Then he's the one who found these mathematical cycles of solar radiation that have led to these great ice ages. Okay, so that's the end of the very beginning of Earth's deep freeze, relating climate and orbital forcing, or the Milankovitch cycles, and then how that affects climate regimes here on Earth. We'll stop this one for now and get on with the second lecture of Violent Earth, Deep Freeze. Okay, let's try another one here real quick. It's amazing to me how I know that I need to go to the bathroom while I'm lecturing, but I still won't stop talking. Okay, everything's solved, and I have a live class here coming in a little bit. So we'll try to get through the rest of, or at least the second segment of the deep freeze conversation here in Violent Earth, starting with glacial deposits. Let's just take a look at some of the record of these glaciations first. Then we'll talk a little bit about the Pleistocene Ice Age, the most recent ice age, and then a little bit about Ice Age beasts. And now when I say Ice Age beasts, you're probably thinking mammoths, giant sloths, saber-toothed tigers, all the great stuff from the movie Ice Age, really like the 6 movies or however many there are. Okay, this is a review from what we looked at in the last portion. Here's the sinusoidal wave of eccentricity of the tilt of the axis, the 41,000 year cycle, and then the 26,000 year cycle of precession. And then here's that combined effect, which again, where we see all of the troughs of these things lining up, then we may see much more extreme climactic changes, right? Where you either have warmer warms or colder colds, right? And then here's each of those 3 visuals stacked up on one another, so you can see the eccentricity, the tilt of the axis, and the precession in that in one diagram. Okay, what this leads to is continental glaciation, and that's when we're referring to an ice age. We're not talking about the glaciers like they're in Glacier National Park. Those are alpine glaciers. Those are glaciers that exist up in cirques or areas way up on the edges of mountains, or those that are on, say, Mount Rainier. Glaciers exist on Earth today, and they're in alpine conditions. Now, as Earth's climate gets cooler, those glaciers do extend out of the mountains, and we have more intense, even during ice ages, more intense alpine glaciation. But during real ice ages, or say during the Pleistocene Ice Ages, it's not just the alpine regions that are covered with ice and having alpine glaciation in the mountains. Instead, there's these gigantic ice caps that flood over the continent as really mile-thick portions of ice that drive across the continent. So these are very slow-moving. Glaciers are not fast-moving features by any means. Sometimes we can be a little bit, I will be a little bit anthropomorphic and talk about them as like bulldozing or crushing or doing these kind of things. But really, that's just the geologist's perspective in trying to fast-forward time, right? Now, these things do bulldoze through the landscape over the course of thousands of years, right? But they are very slow-moving features, and really the major changes that are happening, the geologic changes, are happening during the melting season. So during the late spring and the summer, any glacial area, when there's melting going on, all of the outwash, that's when the real geologic action is occurring. Okay, so vast ice sheets that extend across land masses that are not confined to the mountains, as this alpine glaciation here. But here's a really good image showing the Antarctic ice cap today that is a continental glacier that extends across the whole continent of Antarctica, and then even in over the oceans as sea ice or ice shelves. Okay, so let's take a look at some different glacial deposits and then different glacial features. One of the most characteristic glacial deposits that you're going to find, and these are really common in the Midwestern areas of North America, that's where I'm familiar with them. There's glacial till. Till is defined as this poorly sorted sediment that's been dropped by glaciers. So part of this is a genetic terminology, right? Dropped by glaciers. That's saying how it got there. But there's also this other more observational component, poorly sorted sediment. What we mean by poorly sorted is that the grains that are there are all different sizes. Here's a really large boulder, a couple of angular boulders, and then there's really, really fine grained material in between. What's important to notice about glacial till is that the larger class, the larger boulders and cobbles, aren't really touching each other. Instead, the whole deposit seems to be supported by the finer grained material. We call this matrix supported. The matrix material is what's holding up all of the rest of the more coarse bouldery material. Okay, so glacial till, there's also some of that finer grained material that's contained in that glacial till could be this stuff, glacial loess. But besides just finding loess within the till, we also find these really great accumulations of glacial loess in other areas, just loess by itself. So what is loess? This L-O-E-S-S, that's sometimes, depending on where you grew up as a geologist, people say this a little bit differently. I've always called it loess. This is wind-transported material. It's the size of silt. If you remember back to your sedimentary lecture in lecture 2, silt is different size than clay. And this silt is really, it's glacial flour there in quotation marks, we refer to it. If that glacier is grinding down on bedrock, it is breaking and busting apart that rock into really fine-grained material. This is exactly how flour is made, like in a mill, right? What used to occur is two rocks in a windmill or a waterway or maybe donkeys or something like that going in a circle. Two big stones are moving together like this, and the wheat is put in between them, and it grinds that down to a flour-like consistency. And that's what's happening here is the glaciers are scouring over the rocks to make a flour-like consistency out of that rock. So it's making dust, essentially. But that dust is silt in size, and because it's silt in size, it's easily transported by wind. Well, during the Ice Age, if these glaciers are extending down into northern latitudes, say 48 degrees or 45, 40 degrees latitude, there's a large wind gap that occurs. Here in the North American continent, most of the weather, if you go back to the meteorologic images before, the force of the weather is coming from the west to the east across the continent. That's the direction the jet stream is moving. And that west to east, during the Ice Age, if ice is coming down from northern latitudes, that's cold air. And this wind then is forced through a narrow gap below the glacial area. And then furthermore, there's a huge contrast between the colder and warmer air of the southern areas or more equatorial latitudes. So there's this huge wind gap at the front of the glaciers here, which is kind of like the tundra-like landscapes of north or beyond the Arctic Circle. So this area was completely wind blasted. So all of the glacial flour that is created under these glaciers, and then when melt happens and these rivers just get clogged full of this glacial loess, go to any glacial river coming out of Alaska, like say the Tanana River, is just, it has these colors that are amazing because it's filled with this glacial silt, this loess. So the outwash from this is full of that loess. So it floods, and then after the floods, all this loess is abandoned on these boulder fields, and the wind picks it all up and then drops it into these huge piles year after year after year after year after year. So this is an image of the Palouse Loess up here in Washington that is a very important agricultural soil in the area where people can grow amazing, crazy amounts of wheat on this stuff because of the silt properties, the property for it to, or the property of moisture retention and whatnot. So these glacial loess deposits are very important to us agriculturally, or say in wine country or growing wheat. But also they are inherently a deposit or a observation of glaciers once existing here in North America. Okay, the third one of these glacial type deposits, I think this is a picture by Stephen Marshak. It's from his textbook, Earth, Portrait of a Planet. I think that's where it was from, and I'm not sure if this is his son or if this is some other kid that submitted this image, but I love that he's, this tie-dye shirt is just, showing you, yes, glacial erratic here. But here is what's called a glacial erratic. And that word, erratic, it should spark some imagery in your mind that this thing is like erratic, it's not moving, but you kind of get the imagery of it having been moved around, and it's erratically located. And that's why this was named this way. It was named, I believe, by Louis Agassiz, who's a Swiss geologist noticing alpine glaciation out of the Swiss Alps, and then also areas away from the Alps where glaciers don't exist today. But he saw evidence like this to propose that those glaciers were much bigger in the past. And actually, there must have been larger glaciers, like continental glaciers, even more than that. And I believe he pioneered the term glacial erratic. So glacial erratic are these boulders that are erratically located on the landscape. There's no rhyme or reason why they should be there. There's no big river. There's no other process. There's no glacier there today that would have put those there. They're erratically located on the sides of hills or in the middle of a valley and things like this. So this is an example of an erratic. This is a metamorphic gneiss, the material itself, and that's very different from the erratics that are surrounding it that appear to be granites, or even than the bedrock and the surrounding hills. So not only are they erratically located and out of place geologically, but they're also out of place as rocks in the bedrock. They appear to not be similar to the surrounding rocks at all, which you always expect a river to contain the sediments that are collected from the local hills, right? That are just showing you what the hills are made of. And that's not always the case for glacial erratics. Similar to erratics, but slightly different, are these rocks we refer to as drop stones. A drop stone is it's a glacial erratic that was put there by a more specific process, and that's that they were dropped by icebergs. So instead of a glacier scouring through this area and then leaving behind an erratic, either up in a hill or down in a valley as it's receding, instead, if that glacier had broken off in a large flood, and then that flood water carried it somewhere else in a chunk of ice, and then that ice melted, that rock appears to have dropped out, right? It's a drop stone. Or in another case, like say in the fjords of Greenland, where glaciers are going directly into the ocean, and then those glaciers are calving off, and then icebergs float away, and they have rocks containing them. They eventually melt away, and those rocks drop out to the bottom of the ocean. Again, drop stones, okay? So this is an image of a drop stone out here in the middle of the landscape. And then a few winters ago, we had a lot of snow here in Ontario, and man, they were just scraping snow everywhere from every street and piling it wherever they could, every parking lot. We were running out of places to pile snow out here. And one of these places to pile snow was not all that far from my house. So while I was on my bike commute back and forth that spring from my house down here to Treasure Valley Community College, this huge pile of snow that was here slowly began to melt, and these rocks, landscaping rocks, I suppose, that were accidentally picked up while moving snow, were slowly receding and dropping out of the melting glacier that was here, right? So this is just like a human analogy, right? But it's really the same type of thing. As this large pile of snow melted out, what's left over in that location are these stones that dropped out, that didn't melt away, right? Okay, so we have glacial till as a type of deposit. We have glacial loess as a type of deposit, glacial erratics, and then drop stones as 4 different types of glacial deposit material. Now, if we look at some glacial features, then here's an alpine glacier coming out of this alpine region, and what it has on its margins are all of the rocks that were transported along this glacier, like a conveyor belt, and then dropped at the edge. Now, if this continues to go forward, it's going to keep moving that line of boulders. But if it recedes backwards, so it melts backwards, it leaves that line of boulders at its furthest extent, right? So here you can see this line of boulders, this line of glacial till material, and we refer to this as a moraine. Moraines can be in different shapes depending on where they're located within the glacier. You can either have medial moraines, or what's shown here, here's a lateral moraine, or the terminal moraine, showing the terminus of the glacier. So just interpreting this really quickly, you can tell that this glacier had once been out to here, and then it receded backwards, right? Who knows how far? And then it advanced again to this area, and then receded back, and then has advanced at least to this area. Or maybe this is the area where it's receded back to from here, okay? I can't tell from the image. Now, another couple of features that are shown here are these really weird, characteristic lumpy things here. Lumpy things, I don't know how else to call them. They're called glacial drumlins, and those features may have been glacial moraines. They're made of till, that then as the glacier re-advanced over the moraine, they were kind of spread out, right? So the glacier has actually spread this material into this kind of characteristic shape here, where it's thicker on the edge pointing in the direction of ice flow. Okay, then also what you can see are these lakes that are left behind from the glacial ice melt. Here's an iceberg in the middle of one of those lakes. Here's a river that's from the lake here, from the water melting away, the outwash. There's rivers that extend out to the local low, the local, say, ocean or local lake or body of water. These rivers are important, the moraines are important, these little drumlins. These are all features that we can see here in the rock record that are indications of glacial ice being present in an area even where it's not. So right here, there is no glacial ice present anymore. Now, it's in the distance, but if this glacier went all the way back, we still have geologic evidence for that glacier. Okay, so here's some of these, oh yeah, I should have shown these images a second ago. Here's like the conveyor belt that's dumping off the glacial till. So these are the glacial moraines and in moraine. Here's this idea of a glacial advance and then retreating, leaving behind the moraine. Okay, then there's another really interesting feature called a came. A came is a hill of glacial till that forms in the middle of the glacier. So here's an image of the glacier itself, and here's the terminus of the glacier. And then in the front end of the glacier, where you might have a crevasse, a very deep crevasse, and these rivers that are forming on the top of the glacier because of solar radiation melting the top, if those rivers are collecting some of the sediments from the top and then dropping down the crevasse, those sediments then pile up, and they pile up in these big triangular hills called glacial cames. These are formed by the glacial river dumping sediment into that crevasse. Okay, another is the kettle, or the kettle lake, as it's referred. There are these icebergs that are left behind as it recedes away, and some of these icebergs get insulated by the glacial till. But eventually, they melt away. But all the glacial till that's surrounding them, as it melts away, it kind of caves in to that area, and it leaves a depression behind. And that depression often then can fill with water. And it's an area where you might find lakes or depressions later. So this is a kettle hole or a kettle lake that's left over, or that is made up of those lakes. And here's an image from the Kettle Moraine State Park in Wisconsin, where you do find a lot of these features together. And it's named a Kettle Moraine State Park because of the Ice Age moraine that goes through it, as well as the kettles that litter that area. Okay, so we have kame, kettles, then here's another image of kames and kettles in the Kettle Moraine State Forest, a good example of that. The glacier extending outward and leaving behind the moraine, and then receding backward and leaving behind the kames and other kettle lakes. Then remember the rivers that were going from the outwash area out to the local lake or ocean or something in the far distance. Those rivers also become clogged with sediment, and those rivers can first originate underneath the glacier and carve their path before they're ever outwash rivers. And those subglacial rivers, as they become clogged with sediment, they become clogged with glacial till, essentially. And in areas like Wisconsin, you can find these eskers that are curving across the landscape like snakes. And I think that's part of the origin of the word as snakes. And then here's an esker that's been carved across, and you can see the stratification of that glacial till. Subglacial rivers as eskers, subglacial hills, they're now hills called kames. And then also, what else did we look at? Glacial kettles, which are leftover icebergs that have been melted away. And here's all of these things in one picture. Here's a glacial moraine. Here's an esker weaving back and forth. Here's a kettle lake, and then one of those aforementioned drumlins as well. Okay. Remember, it is the combined effect of all of these things that are leading to major periods of glaciation. Just want to always have this in the back of your mind, because I think that's really important. Again, I mentioned in the earlier portion of this lecture that we have these misconceptions about glaciation, maybe, or ice ages, that maybe it only happened once, or maybe that climate is only based on amounts of carbon dioxide. But really, I want you to keep this effect in the background, that it is not just carbon dioxide. Remember, that's a buffer. It's like putting blankets on. But instead, it's solar radiation. And this doesn't just happen once, right? That you can imagine these waves overlapping again and again through time, as we saw in the glacial regimes picture at the end of the last video. Okay, leading to great continental glaciation. Okay, so the most recent of these glacial time periods is the Pleistocene. This is one of the, I guess, really neat recent period of geologic time, or I say recent epoch of geologic time. And this extended between 2.5 million years ago and up to the Younger Dryas period or time, 11,700 years ago. And that's not necessarily right at the last glacial maximum, but the Younger Dryas was a period of rapid glacial re-advance. So it had receded back for a time period, and there was a re-advance, and then now glaciers have advanced basically as far back as they are today and continue to advance backwards. The Pleistocene, and here in North America, was a great time of reorganizing the drainages of North America. As these glacial caps scoured across North America, they fundamentally changed the drainage system by both scouring this land and changing the system, as well as all of the outwash that propagated thereafter, and as well as lowering some of the mountains by alpine glaciation. So what's shown in this image is the areas of Mississippi drainage, ancestral Mississippi drainage, mostly in the southern United States. But of course, today, the Mississippi drainage covers a much more vast area all the way up into Canada, both in just above Montana, as well as inland a little bit in parts of the Great Lakes, though parts of North Dakota actually drain into the Hudson Bay. But the Mississippi, just as one example, went through great reorganization as a drainage during the Pleistocene glaciation. Now, of course, when I say Ice Age, you probably think well, cold and ice caps and maybe cavemen, Neanderthals or something like this, right? Which are, which is also a misconception, but it's fun, right? This is kind of what we think of as the Ice Age. We're large Ice Age beasts and mountains of ice that existed. But there's also, again, that misconception that it happened once in the past, and that was far, far back, and then they've melted away and they're gone. We're out of the Ice Age. And I think this is also upheld by some of this popular media as well. I think, interestingly, one of these movies suggested that the Ice Age caused the end of the dinosaurs, something like that, which is also not true. Dinosaurs went extinct by an asteroid impact, as we'll talk about in the next couple of weeks in Violent Earth, 65 million years ago. And this is 2.5 million years ago by the time we're talking about this Pleistocene glaciation. So much different areas of time we're talking about. But let's look at these Ice Age beasts a little bit, because this is one of the most enigmatic features of the recent Ice Age. So we've covered glacial features, glacial deposits. We've done enough of the looking at the geology. Now let's look a little bit at the paleontology. This is a really good compilation image of a whole lot of the glacial beasts that existed. You have like your woolly mammoths and your Columbian mammoths, things like mastodons and cave bears and cave lions, saber-toothed animals. There were a whole plethora of saber-toothed animals, North American horses, the glyptodon, or the kind of giant armadillo looking thing, ancestral bison or ancient bison that were much more massive than today's American bison, camels, North American camels, large elk. Let's see, then your Megatherium, the giant sloth, and I want you to notice that this giant sloth is about as tall as a mammoth. I think this is striking and this is amazing. Now, I'm not a paleontologist by background. I'm a geologist, hard rock. I like looking at the really hard rock features. But I can't avoid that this stuff is just really cool. These creatures are really great. I'm no expert in these creatures, though. So I'm going to kind of leave that for you to discover a little bit more on your own, all of the individuals of these creatures. But here's just kind of a broad look at some of the exclusively North American mega beasts that existed during the last Ice Age. And I refer to them as mega beasts. Now that might be a little bit of an overstatement or something, but many of these things are what are referred to as megafauna, or animals that are mega or massive in size that were during this time. And then at the very end down here, you can see the Ice Age hunter, the Homo sapien for scale size back here. But also there's a common hypothesis of the megafaunal mass extinctions. Well, the megafaunal mass extinction is an observation, and the hypothesis is that Ice Age hunters, wherever they encountered these megafaunal beasts, encouraged their extinction. They may have already been receding in their populations, but they also had some sort of impact to them. Okay, I only have a couple minutes here until my live class starts. Here's one of these animals, not from North America, the gigantic kangaroo, the Prosoptodon. Here's one of the gigantic terror birds, the Titanus. Look at this thing, bigger than a human. You could bite your little head off right there, no problem. Scary to me. And then the Haas eagle. Here's one of these gigantic Haas eagle that appears to be coming down to capture some of these larger flightless birds. I mean, the Ice Age, just like the cartoon movies show, was a time of beasts that are relatively foreign to us. Pretty amazing. All right, this dose of violence today, besides the mega beasts, I guess I forgot to hold up the mammoth tusk that was found here locally that we have. Very important to check that out. Today's dose of violence brought you to by Louis Agassiz, the Swiss geologist that pioneered the idea of there being past ice ages. And funny enough, his gravestone where he's buried is made of a piece of glacial moraine that was extracted from near where he grew up. I should say one thing about Agassiz is that though he is very well known and has left this legacy behind of pioneering the idea of ice ages, Maybe something that would have been noticed whether he had done it or not. Probably would have. Geologists are pretty sharp fellows, pretty sharp girls and gals, or guys and gals. But also, unfortunately, Louis Agassiz was also very ingrained in some of his Eurocentric perspectives, and he is very criticized in having some scientific racism implicit in some of his writing, and this idea of polygenicism, or that different races of humans were actually originated differently, that there was a basis to racism, a fundamental biological racism. Racism. So a lot of those ideas, of course, have been put away, right? We know a lot of these. We know better today as a scientific community, and hopefully as a global society of humans. And unfortunately, this gentleman of his time, there were many people of that time that supported that type of stuff. And so, by acknowledging him today and his work on glaciation, I'm not acknowledging him because of a lot of these other very poor ideas that he had. Okay, so that's the end of the second segment here of deep freeze. And in the next segment, we're going to explore even larger ice ages that have occurred here on the planet Earth. Okay, all right, thank you, and we'll see you again in a minute. Okay, we're back after astronomy class. It's 8 o'clock at night. Well, we got to finish this Violent Earth deep freeze material here. Right. Quality looks like it's changed a little bit. I hope I changed some lights. I don't know. It's still washed out. All right. So the last portion of this deep freeze material, we're moving from the Pleistocene, which, remember, was really recent in geologic time. It only ended a little over 11,000 years ago. Starting about 2.5 million years ago. Now we're going to go way back in time, way back to a time called the Proterozoic. Okay, I think I have some numbers on here that shows you what we're talking about with Proterozoic. But the Proterozoic is the latest or the most recent of the time period that we refer to as the Precambrian. So the Cambrian, if you remember back to lecture 1 in the geologic timescale, started 542 million years ago. And it's since then that we have the explosion of life and all these great creatures. And then everything before that, remember, we refer to as the Precambrian. Well, the Proterozoic is the last segment of, well, and it's a pretty long, substantial segment of the Precambrian. But basically, there is not much for life going on here. There's very little going on. We do have, as we'll talk about in a few weeks in Violent Earth, there are bacteria, cyanobacteria, and a little bit of some creatures in the Ediacaran, the very last phase of the Proterozoic. But for the most part, the Proterozoic, there's nothing going on, not much. Stromatolites and bacteria, very little. And what this is the Neoproterzoic specifically, which is the Neo being recent, the last portion of that Neoproterozoic stuff. We'll take you through a little bit of the evidence, the Neoproterozoic evidence for this glaciation, show you the evidence and its distribution. And this event is what's referred to as Snowball Earth. Snowball Earth. I think that's a pretty great and fantastic name. And that name, as you can see from this diagram, comes from, this image comes from the idea that the whole Earth was under a deep freeze. From pole to pole, all the way glaciation down to equatorial latitudes. And we're not talking alpine glaciation, continental glaciation, all the way down to equatorial latitudes. And we have evidence for this. Evidence in the rock record of glacial till at equatorial latitudes or near equatorial latitudes. Okay, so this segment shouldn't take all of that long. The 3 minutes of introduction probably took longer than it really needed to. All right, this is where we were after the first segment was focusing on the Milankovitch cycles And the areas where the sinusoidal curves actually overlap to make extreme climate conditions. And in the first lecture, we also looked at there are several climate regimes, the ice house, the hot house, and then in between, the cool and warm greenhouse. And through time, we do notice that not only do the Milankovitch cycles mathematically line up, but we also see evidence in the rock of glaciations that are fairly well known. The one that we just talked about, the Pleistocene glaciation, the most recent glaciation is here. But also back here during the later portions of the Paleozoic, the Permian Ice Age, a pretty deep freeze there as well. And then further back, the late Proterozoic Ice Ages, that's the topic that we're getting to here. But I want to briefly point out that there was an even earlier Snowball Earth type of Earth experience, the Huronian glaciation, that occurred even further back, about 2.5 billion years ago in Earth time. Now, again, I'm not gonna touch that one or these two, but instead, I want to look at some of the evidence for the Neoproterzoic glaciations that we refer to as Snowball Earth. Okay, Proterozoic from 2.5 billion years ago to 542 million years ago. Looking at the youngest of these sediments, the Neoproterozoic, in several sections around the world, it is identified that we have some of these strata, like this picture here, that's showing what's referred to as a diamictite. So a diamictite is it's a rock itself, okay? And this diamictite, God, I'm not going to be able to show you on here. It's far too dark and far poorer quality. But this rock, I assure you, is a piece of diamictite. And think glacial till from that second lecture, the materials of moraines that we looked at. And this is poorly sorted material. Not just poorly sorted, but the matrix, the finer grained silts and loess make up most of the rock. And the larger chunks, the cobbles, the boulders even perhaps, seem to float around in this matrix, or they're supported by that loessy, silty matrix. So this, just like this piece of diamictite, and others around the world, this is from Death Valley, California. It's where I was fortunate enough to do my master's thesis mapping in an area referred to as the Amargosa Chaos. And there's a formation there, the Kingston Peak Formation, that's exposed, that's late Neoproterozoic in age. And it's been noticed for a very long time that as part of that Kingston Peak Formation, there are at least two major pulses or major segments, major probably 2 to 3 meter thick sections of this glacial diamictite. And that's what's shown here in this lower strata. And then there's a geologic contact between this upper strata, this sort of more cream-colored carbonate rock that becomes very important to the story as well. We'll talk about that in a second. Besides, in the Kingston Peak Formation, here, besides there just being these glacial diamictites, at another regional section, now this was not in the same area in the Amargosa Chaos, this is in Sperry Wash, a little bit further south in just outside of Death Valley National Park. There's a section of the Kingston Peak Formation that is mostly marine shales, marine siltstones, very fine grain material, which is very different from this coarser grain material. But this fine grain material, it's all fine. You walk by it, it just looks like nice shales and a huge thick pile. Except the odd things that we get here, the gigantic boulders in this case, the whopper, as this one is kindly referred to by all those geologists that visit it. It's actually kind of a famous boulder, if boulders can be famous. But the whopper here shows, and all of the other large, and I'm not just talking cobbles, but they're almost all boulder-sized materials within these shales are drop stones. Okay, now why aren't they just big rocks that are stuck in the middle of these siltstones? Well, so first of all, in this environment that's depositing silt by suspension settling, if you remember back to sedimentary rocks, the finer grained materials are settling out of suspension, raining down in that lake or that ocean, and settling on the bottom. That's rudely interrupted by these big chunks, right? So this is a calm setting, and then all of a sudden there are these big chunks in there that could only be transported by higher velocity streams or higher velocity floods or something. But there's no evidence of floods, there's no evidence of streams, anything like this. It's calm, and then all of a sudden you get a big old rock in the middle. Okay, now furthermore, underneath of these drop stones, the silt underneath is actually deflected, as if this rock hit the silt and depressed them a little bit and made a sort of a little divot. And then the rest of the silt for, days and days and years and thousands of years afterwards, accumulating around this, sort of lap up on this and overlay the boulder here. So that's a piece of evidence, the lag underneath these boulders, to suggest that they are actual drop stones, that these things calved off of glaciers, icebergs calved off of glaciers, and were floating around buoyantly in this nice calm settling ocean. And then as that iceberg was melting, boop, out drops the drop stone and falls to the bottom of the ocean to deflect those sediments out of the way. So we have perfect drop stones in the middle of these silty sections of, in this case, the Kingston Peak Formation, which is in modern-day Death Valley, a desert, right? Now, underneath of the Kingston Peak Formation, it's not very well shown here in this segment of the Amargosa Chaos. Everywhere underneath the Kingston Peak Formation is a unit then called the Beck Spring Dolomite. A dolomite is like a carbonate. It's a limestone, as we went over in sedimentary rocks. And limestones, remember, are made of calcium carbonate. So this calcium carbonate, very likely, or at least all the evidence we can gather, precipitated in an ocean, in a marine sediment. It's hard to determine this sometimes when there are no fossils, right? This is the Proterozoic. We can't find any trilobites. We can't find any bivalves. We can't find creatures that we know are marine, but all of the surrounding context suggests this is a marine environment. And other stratigraphers have worked on this much more than I ever have. So you have a dolomite or a limestone below, and then the next unit is the Kingston Peak Formation, which in some of the facies, some of the lateral areas contain drop stones, and some of the areas contain glacial till, basically, these diamictites, or what we might refer to as glacial diamictites then, if they have glacial, if we're suggesting they have glacial influence. Now, limestones form in more tropical environments. If you go back to the climate discussion we were having a few videos ago, areas where there is high enough energy, enough solar radiation, that in the water column there's enough energy available for calcium and carbonate to bond together to form a calcite crystal. And then those settle down to the bottom of the ocean. Now, this can happen in a wide variety of marine environments, but it's the tropical environment that these accumulate much more massively, or they accumulate more rapidly. And then also within the Beck Springs dolomite, in this case, the Beck Springs limestone, there's some evidence of algal mounds or algal layers, or what are called stromatolites, which are some living remnants. So there may have been bacterial algal colonies that are living in these areas as well, which need much more tropical environment, or a much more warm environment. So just by context of the limestones, this would suggest that these are tropical marine sediments. And then boom, right on top of them, diamictites, glacial diamictites and drop stones, and so on and so forth. Okay, so it's that evidence, at least from here in the Death Valley region in North America, that's part of the larger story, the global story, suggesting a global glaciation. If it was just in this one site, we might suggest maybe these are some really large mountains they were experiencing alpine glaciation and going into a local ocean, say at equatorial latitudes. But there's much more than just the Death Valley section. This is a section in Namibia where there is a drop stone here. Clearly see the deflected sediments. Okay, another section here with a drop stone. These aren't boulder size. These look more like pebble to cobble size, but again, deflected sediments around them, and then sediments layered on top. And then here again from Namibia, these are images from Paul Hoffman's site, snowballearth.org. In this Namibia section, again, more diamictites. Here's larger boulders and cobbles that are in a matrix-supported deposit. So it's very clear that it's not just one area at this time in the Neoproterzoic time frame. At equatorial latitudes, the Earth is experiencing glaciation, not just in what is modern-day Death Valley or modern-day Namibia, but there are also sections of these spread around the world and distributed around the world. Here are some of these in yellow. The older of these glaciations, there's actually two pulses of this. I'm not going to go into detail on that, but one of these is called the Sturtian glacial interval between 730 and 700 million years ago. In yellow here are these are sediments of diamictites, or also of glacial origin, glacial evidence, right, like dropstones. And then in red here are banded iron formations, and we'll take a different lecture, a different chunk of this to talk about the origins of banded iron formations. But these are sediments that, as the word suggests, they have iron within them, but they're also oxygen-rich sediments. And so those have different implications in context globally in violent Earth, but also here in when we're talking about Snowball Earth. The important thing here is to look at the great distribution of these glacially derived sediments around the world. This isn't one location we're talking about. This is global phenomenon. And many of those were likely at equatorial latitudes as they were being deposited. So one way, as I suggested, we could do this lithologically, that the limestones were probably marine limestones. And so we have tropical marine limestones, and then on top of them, glacial deposits. But also, there's a technique using cores of materials, rock cores, to get their paleomagnetism. So I won't dwell on this in this detail for too long, but this idea was originally proposed by Joe Kirschvink, I believe out of Caltech, that pioneered this technique of paleomagnetism, or at least was very implemental in advancing its uses. And the Earth has a magnetic field, and each of the iron-rich sediments, whether this is an iron-rich crystal of magnetite in a magma, or banded iron formations, or otherwise, iron will align to magnetic north. So we have little tiny north crystals that are freezing into place in different times in geologic history. So if we can collect those materials and then read their original orientation, we may be able to then reconstruct where those continents were, northern latitudes or more southern equatorial latitudes, okay, by looking at their paleomagnetism. Because after all, the magnetic orientation doesn't tell us longitude, it tells us latitude, right? So we can at least back that material. I think that there are also techniques that more refine this, that can find a more precise location of the continent. So here, there's a couple of pieces of evidence then that these were equatorial latitude sediments. You have paleomagnetism, as well as just the lithologic context of marine sediments. So this is the reconstruction, or at least one of the popular reconstructions. This is from the Marshak textbook, Earth, Portrait of a Planet, that I mentioned earlier. The same textbook I used for the geology courses here. And this is amazing to me. The continent at that time, or the continents, were assembled together mostly, loosely, as a supercontinent called Rodinia. We'll talk about supercontinents again later in Violent Earth course. We're oftentimes familiar with the supercontinent Pangaea that opened and left the Atlantic Ocean. But before Pangaea even, all of those continents were assembled in sort of a slightly different way, very similarly along the Atlantic margin, as a different supercontinent referred to as Rodinia. And as Rodinia was breaking up, some of the faults, as this was breaking up, allowed these sedimentary basins to form during that breakup. And it's in some of those sedimentary basins that these deposits, these glacial deposits, were deposited into. So we're very fortunate in the rock record that we have such a great record of this event, because all of this pulling apart of the Earth's crust left these depressions for these sediments to deposit into, and then preserve until later today, right? Until today. So this diagram is showing the larger, massive supercontinent that spans across the equator, that had, of course, mountain ranges where the things were stitched together, and you have orogenic uplift and creation of mountain ranges. But also, as these places are splitting apart and those mountain ranges are getting torn down by normal faulting, you have areas for those sediments to deposit. Now, I want to point out this little green band that's right here, that maybe these areas were experiencing alpine glaciation, but the rest of the equatorial latitudes, just because of a meteorologic phenomenon, may have stayed not permanently frozen, or maybe somewhat thawed or slushy. Some people have actually suggested that this wasn't Snowball Earth. Instead, this might have been Slushball Earth, or something like this. Okay. Now, the point here is that we know a lot about the evidence for this event existing, but we don't know all of the details of this event. But just because we don't know those details doesn't mean that we don't have that evidence for something large and catastrophic occurring during that time. Catastrophic if you're maybe a living organism during those times. Now, I want to point something out here, is that the land is glaciated, constant of the glaciation, but just like Antarctic ice shelves or the northern sea ice over the North Pole, there is ice over the over the oceans as well. This is important because the sea ice then is making a boundary between the gases of the atmosphere and the gases of the ocean. Okay? Now, chemically, the ocean and the atmosphere are continually exchanging gases between one another, and are in some sort of chemical or gaseous equilibrium. I like to make the analogy of a soda, right? Sodas, when you get them brand new outside of the cooler at the gas station, they're chock full of carbon dioxide. That's what makes it fizzy, right? And that's part of why we like the sodas, is they're the fizzy drink besides all the sugar in it. Now, that fizzy stuff is under pressure in the soda. Notice that the soda bottle is it's a little firm and more hard before you open it. And as soon as you open it and release that pressure, the gases begin to exhaust. Okay? Now, the gases, as they're in the soda, because they're under pressure, they can be dissolved within the soda, within the liquid. But as soon as that pressure is released, the gases want to escape. And then as soon as that cap is undone and is introduced to the atmosphere has much lower amounts of carbon dioxide than the atmosphere within the bottle. So between a soda, there's inherently a difference between the carbon dioxide content of the soda and the carbon dioxide content of the atmosphere. Now, what happens if you leave the cap off of the soda for a day or for a couple of hours? All of that carbon dioxide dissolves and goes into the atmosphere. Why? Because there has to be an equilibrium between the liquid and the in the surrounding atmosphere, or at least there doesn't have to be, but that's the law of equal gases. Now, why is this important? It's important because the ocean is a natural carbon dioxide sink. As carbon dioxide from volcanoes, or today from anthropogenic carbon dioxide emissions, the oceans are a great sink for that material. The oceans are starving for it. Well, maybe not starving, but they are so great at sucking that stuff in and then making stuff with it, like calcium carbonate or calcite or limestone. Okay, so during times during times when there's carbon dioxide in the atmosphere, as always, the oceans can absorb that carbon dioxide and sequester it as stone and lock it down there at the bottom of the ocean. So it doesn't matter how much volcanoes are putting out, the ocean can suck it in. Well, what about our emissions, anthropogenic emissions? Yes, over the long geologic time frame, the oceans are able to do this, right? They're able to suck all this in. So the oceans inevitably will absorb a lot of this carbon dioxide from the atmosphere as limestones, but it doesn't happen overnight. It doesn't happen very quickly or fast. And also there has to be a pH balance in this situation. So if there's too much carbon dioxide in the water, then because carbon dioxide and water make carbonic acid, then the acidity is too high, so the pH then is too low, and calcium carbonate, the mineral, can't form. So if the acidity is too high, if there's too much carbon dioxide there, then that impedes the making of calcium carbonate. So again, there's a balance between them, and this is a slow geologic process. Okay, coming back to Snowball Earth, this sea ice is really important as it cuts off the chemical equilibrium between the atmosphere absorbing in carbon dioxide from volcanism. Well, as these continents are ripping apart, or maybe even continental convergence on the margins where there's arc volcanism occurring, there is a large amount of volcanism that's putting carbon dioxide into the atmosphere. Okay, I guess just quickly, here's one of these sections that has the diamictite and then the limestone on top of it, and then the diamictite and limestone on top of it. This one is here referred to as a cap dolomite or a cap carbonate. Okay, so here's a picture of a volcano in Iceland. This was 7 or 8 years ago. There was a large volcano in Iceland that, when it erupted underneath the ice sheet in a phreatomagmatic eruption. It was the lava was interacting with the ice cap and making steam. So the explosion was even the eruption of magma or of lava was bad, making ash, but also all the steam eruption was pretty bad too. Now, so imagine this occurring on the margins of the continent of Rhodesia or anywhere else, and you have carbon dioxide being pumped out into the atmosphere, pumped out into the atmosphere, pumped out into the atmosphere. But because the ocean out here is cut off, right, by the sea ice, that atmospheric carbon dioxide can't be absorbed into the ocean very easily, right? It has the ice barrier to go through, so there's a cutoff of the carbon dioxide in the atmosphere and the carbon dioxide that could be sequestered in the ocean. So the ocean becomes starved of carbon dioxide, especially in these tropical marine environments where limestone was depositing, right? Like the Beck Spring Dolomite. Limestone is depositing, it's nice and tropical, nice limestones, carbon being absorbed from the atmosphere, like business as usual, it's just fine. Then you have this absurd glaciation that cuts it all off, and instead the deposits where they are depositing are either silts with drop stones, evidence for glaciation, or some of these glacial diamictites that are evidence of the end of a moraine, a glacial moraine. But no limestones, right? No carbonates. Then, right, as the ocean and atmosphere are chemically decoupled by this event, the continuous outgassing of all of this into the atmosphere, right? You know what happens when parts per million of atmospheric carbon dioxide increases? What do we talk about today by increasing anthropogenic emissions. We are talking about that being a greenhouse gas, absorbing infrared radiation, and warming the atmosphere, right? Now, what better to stop a global glaciation than a warm atmosphere? So after no sequestration of carbon dioxide, the carbon dioxide builds up in the atmosphere and builds up and it builds up, and then we have a runaway greenhouse effect, right? That runaway greenhouse effect begins to warm the planet. Now remember, we're still in Milankovitch cycles, so whatever is happening with those, maybe we're coming out of those cycles in some way, maybe the tilt, the obliquity is changing in these 11,000-year cycles, or these larger cycles. Conditions are a little bit better orbitally for this to occur anyway, but if you add all these blankets on top of that cold person, they're going to warm right up. So all of this buildup of carbon dioxide causes a runaway greenhouse effect, and the glaciers recede. The ice recedes away, and then as the sea ice recedes away, and there's a ton of carbon dioxide in the atmosphere, the oceans suck it right back up, making a carbonate or a limestone, a dolomite even, on top of those glacial diamictites, or the dropstone deposits, on top of the Snowball Earth deposits. So it goes in the Death Valley sequence: limestone, diamictites, glacial evidence, limestones, right? So again, those cap carbonates are really important to the story, and they fit in really well with the knowledge that carbon dioxide had to have built up in the atmosphere if the atmosphere and ocean were decoupled chemically at that point. Okay, back to this picture. It's shown like 3 or 4 times here already, but I really like it because I took it, right? This is an area that I'm really fond of. Glacial diamictite contact with the noonday dolomite, or this carbonate, that is evidence of the ocean reabsorbing that carbon dioxide. Okay. Now, again, I mentioned that there were 2 pulses of this. There's the earlier Sturtian glaciation, and then it happened again. Oh man, didn't we solve all the problems here? No. Remember, it's the orbital forcing that's the dominator, that's the main thing going on. So even if all that carbon dioxide had built up, melted away the glaciers, the oceans suck it all back in, and then we're left with lower amounts of carbon dioxide, and those orbital conditions maybe coming back around on the cycle, on one of the larger eccentricity cycles, 100,000-year cycles, and gets thrown back into glaciation, the Mariana glaciation. Now, both of these together, I want you to notice the name of the time here, the cryogenian, cryo for ice. It has been long noticed that this time period is dominated by glacial deposits. I think it's fine on the first order for violent earthers, right, and for us to call the whole event Snowball Earth. It's good to understand the detail that there was a gap in that snowball activity. But at the timing of about 700 million years ago, Earth experienced a deep freeze where there were glaciers that extended down from the poles to equatorial tropical latitudes. Okay? And the whole planet was under glaciation, or at least significant portions of it. Now, I like this diagram. This also comes from Paul Hoffman's website, the snowballearth.org, and this shows what was mentioned earlier, the Ediacaran time period. And these bar graphs up here are showing faunal diversity, animal diversity. That we see a huge jump in animal diversity preserved, the fossils that are preserved, here in the late Ediacaran. And then we see, boom, another rise during the Cambrian, and boom, yet more rises throughout the Cambrian. So, in some way, it's very possible that these pulses of glaciation had something to do with setting the stage for these early organisms to get a firm foothold here on Earth. There's a last pulse of glaciation here in the mid-Ediacaran that may have been the final kind of insult to injury, right? And there's the saying, what doesn't kill you makes you stronger. Now, remember, evolution doesn't happen on the individual basis. So just because this individual didn't die during this glaciation and they became stronger for some, I'm suggesting, and others have suggested, that it is overall the species diversity, the things that made it through, had the genetic code, the genetic variation to do well thereafter. So those things that survived with genetic variation to do better after they didn't die on the other side. Okay, I think this is a wonderful, fascinating story. And remember, here in Violent Earth, we're not just telling stories. I'm not just making this fantastical mythology up. This is scientific knowledge at its best, right? That we have individual, independent pieces of observable and verifiable evidence from multiple sources over tens and hundreds of years that are all pointing to the same probable conclusions with evidence. Okay, amazing stuff. Okay, so that is the end of the global deep freeze, having gone through glacial deposits, Milankovitch cycles, the Pleistocene glaciation, Pleistocene Ice Age beasts, and the Neoproterzoic glaciation. So that dose of violence, particularly this last section, is brought to you by Paul Hoffman, the Canadian geologist that I mentioned a few times. He was not the founder of this idea, but he has certainly taken upon it himself to advance this in any way that he can possible. There are plenty of others that work as well on this problem and on these sediments. There are several, this is still a debate. This is not a Snowball Earth for sure. This is a, what can we learn more about the details? So it's indisputable that there was glaciation that occurred, and some of it at equatorial latitudes, but whether this was Snowball Earth or whether this was individual areas, but a whole lot of them, is yet to be determined. But Paul Hoffman has been doing his best to advance this over at least the period that I've been an aware, knowledgeable geologist. Okay, so that ends the fourth segment of Violent Earth, Deep Freeze. And the next segment, we're going to kind of take a step back from this large global catastrophic violence, and we're going to go to a bit of violence that's a little bit more, I want to say, real for you and I, right? Volcanoes and volcanism. Okay, so first we're going to start off with kind of average volcanism. I'll give you a few details, geologic details on how volcanism occurs, how melt even forms in the interior of the Earth. And then we'll take that background of normal volcanism, and then we'll look at the stuff that's big, violent volcanism, right? Called super volcanoes. Okay? So that's it for today in Violent Earth, and we'll pick it back up on the fifth segment with volcanism. Till next time.